Thank you. Okay. Let me hide my little meeting controls here. I think Elliot mentioned we'll save questions till the end, but I won't be seeing the chat while I'm talking here. So there we go, hide video panel. Okay. Thank you all for being here today. It's unexpected how emotional it makes me seeing people from all different walks of my life, from my childhood friends, my high school physics teacher, my friends in Chicago, and of course my family here in Michigan and Illinois, Utah. So today I'll be presenting my work. The title of my dissertation is Evaluating Optimality in the Control of Wearable Robots. Thank you to my committee, co-chairs David Remy and Elliot Rouse, as well as the rest of my committee, Deanna Gates and Noel Perkins. So high-performance wearable robots, like the fully powered lower limb exoskeletons and prostheses pictured here, have the potential to assist people during walking. These devices use motors, or actuators as we call them, at the joints to provide assistance to the wearer. Now, these prostheses may be used by people after amputation, and the exoskeleton might be used by someone after they've sustained a stroke or a spinal cord injury, or someone with any type of neuromuscular condition that affects their walking. Yet, despite the promise of these devices, very few are actually on the market as commercial devices. So as of right now, there are two powered prostheses available, the Össur Power Knee and the Ottobock Empower Ankle, which is formerly known as the Biome, which is how you will probably hear me refer to it as. And then there are several of these full lower body exoskeletons. The Indigo is pictured here, and these devices are mainly used as rehabilitation tools. So this means that currently, the vast majority of robotic exoskeletons and prostheses are still in research development. These include devices like soft exosuits, combined robotic knee-ankle prostheses, and ankle exoskeletons. And I want to point out about these devices that they include those that can be used as assistive technology and also those that can be used for augmenting existing neuromotor capability. Now, with research devices like this, we can do a lot of interesting experiments, learn quite a bit about how robotic assistance affects people during walking. But of course, the overall goal is the translation of these devices, getting them out of the lab and into the real world where people can use them at home or in the clinic. So the robotic hardware systems themselves are becoming lighter and more compact. They have longer battery lives, and all of these hardware advancements are helping lower the bar for translation. So then what's stopping the translation of these research devices? Well, through an engineering lens, one of the reasons is that the control of these devices is challenging. I mean, simply from a robotics perspective, you can imagine that these devices are complex, multi-degree of freedom robots that present an interesting controls challenge. But for us, the control problem is even more complex because these robots interface directly with the human user. So not only must we carefully design and tune a robotic controller, we must also provide safe and effective assistance to the human body. And as anyone who's worked with humans knows, they are inherently unique and unpredictable. And so in order to really provide a benefit to the user, we need to prioritize personalized control of these devices. So the overarching goal of my doctoral research has been to investigate the question, how do we provide users with effective assistance from robotic exoskeletons and prostheses outside the laboratory environment? And the most important word here is effective. What does it mean for robotic assistance to be effective? So the way that I approach this question in my research can be described through this kind of generalized framework. So I would say to design effective assistance, we must first ask ourselves, what's the objective of the assistance? What do we want the robot to do, and how do we want it to affect the user? And I'll expand on this later in the talk, but this objective could be any number of things, like reduce the user's energy expenditure, or increase their walking speed, or promote healthy biomechanics. We must be able to reliably measure whatever objective that we're interested in, and also make sure that we can do it outside the lab. We need to design a controller for the robot that meets the objective, and then finally evaluate the human-robot system to see if we actually achieved the goal. And of course, this system feeds back on itself, and insights from each step inform the future iterations. So this process is what I think of as the optimization of control systems for assistive robotic devices. And by addressing each phase of this pipeline individually, as well as considering it as a whole, I believe that we can design not only effective controllers, but optimal controllers. And in this context, the optimal controller is the controller that meets or achieves the objective for each individual user. So I'd like to ground the theoretical framework I just proposed with an example from ankle exoskeletons from the literature. So one of the most common objectives for device optimization, and especially in exoskeletons, is to reduce the metabolic cost of the user. Now, I'll be discussing metabolic cost quite a lot in the rest of the talk, and you'll hear me use it interchangeably with energy expenditure. So to measure metabolic cost, right now it's most common that we use indirect calorimetry. So the user wears a breathing mask that measures their gas exchange, and we calculate metabolic cost using a ratio of oxygen consumption and carbon dioxide production. So once we have the objective, we have to design a robotic controller in order to meet that objective. So as an example, I will be using data from the Gall's paper in JNER, in which users wore pneumatic ankle exoskeletons that are pictured there on the left. So in general, when I talk about the controller for a robotic device, I'm generally referring to the assistance profile or assistance trajectory. So in this example, the assistance trajectory is the ankle torque, the exoskeleton torque, as a function of the user's stride or gait cycle. So in order to design the assistance profile, we define it based on a set of parameters. So in this example, there are two parameters that define this assistance profile: the onset of the actuation, or when the exoskeleton begins to assist the user, and then the magnitude of the torque burst. Now, modifying these parameters changes the shape of the assistance trajectory and ultimately will change how the device affects the user. Now, because we're trying to achieve a specific objective, as I told you in this case, the objective is reduce the metabolic cost. This means that we have to tune the parameters by measuring the objective. So in this study, the authors opted for a brute force approach, where they had users walk at 10 different combinations of actuation onset on the x-axis and power or magnitude on the y-axis. This data collection allowed them to fit a surface function to the data. And then the color corresponds to the change in metabolic cost from the zero work condition. So finally, to identify the optimal parameter settings, the authors identified the settings that corresponded to the lowest energy cost, which is the controller that fulfilled the objective they were designing for. So this whole process, this kind of brute force approach to device optimization, can be really effective. You can identify optimal parameter settings this way, but you can imagine that it quickly becomes infeasible with increasing numbers of parameters to tune. And finally, continuing with data from the Gall paper as an example, the last step in the pipeline is to evaluate the human-robot system. So in this study, they also looked at how muscle activity changes with different parameter settings, but you can examine any quantities you're interested in, like center of mass mechanics, kinematics, or even more user-specific quantities like preference or perception. Really, the important thing is to evaluate the whole system to see if you met your desired objective, as well as observe any other effects of the robotic assistance. So as an alternative to the brute force tuning method, another way to tune the parameters of a controller is through a process called human-in-the-loop or body-in-the-loop optimization. Now, this method has so far been implemented with the objective of minimizing the user's metabolic cost of walking, but this framework can be applied to any number of objectives in a more general sense. So in this process, the user walks wearing an assistive device, which is programmed to provide assistance according to some set of control parameters. This is depicted in the orange in the bottom. So while the user is walking with a specific set of parameters, their metabolic cost is measured using indirect calorimetry. Then to close the loop, based on those real-time measurements of metabolic cost, an online optimization algorithm will iteratively choose the next parameters to try. And then this process will continue in the loop until the optimizer has converged on the energetically optimal parameter settings. So in the context of this general framework I proposed, human-in-the-loop optimization represents a continuous loop of measuring the objective and updating the design of the controller. Now, this process has been implemented in a few different papers, and so far with this approach, it seems that high energetic savings are possible, especially compared with metabolic cost reductions of hand-tuned controllers. For the control of exoskeletons and prostheses, this is a relatively new concept. The first paper came out in 2015, but many researchers are excited by its potential, and it's a very active field of research. So far as a field, we have focused a lot on using metabolic cost as an optimization objective. And a lot of our research has been done in the lab using tethered exoskeleton and prosthetic systems. We've been testing treadmill walking during steady state conditions. And this, of course, has been groundbreaking and important research that has produced a lot of foundational results. But as we think about the way that our lives look, and the different situations where people may be using wearable robotic systems in their homes, during exercise, in their jobs, we need to be able to translate this technology outside the lab. And this includes expanding our definition of what it means to be optimal, as well as developing tools to measure objectives outside the lab. So as I mentioned, overall, my doctoral work has focused on this question: how do we provide users with optimal assistance from robotic exoskeletons and prostheses outside the laboratory environment? So to address this very broad question, I completed 4 main projects, each which address different phases of this pipeline. The individual projects from my dissertation are described over 4 chapters. In chapter 2, I evaluate the impact that changing the power setting of the Biome commercial powered ankle prosthesis has on the metabolic cost of transport of individuals with amputation. In chapters 3 and 4, I investigate an alternative method for estimating metabolic cost, which uses portable wearable sensors. And in chapter 5, I investigate user preference as an objective for the control of lower limb robotic exoskeletons. For the sake of time today, I will not be able to discuss my work from chapter 2 in detail, but this project was completed under the advisement of Dr. Deanna Gates, and this study has been published in scientific reports. So I would like to start with my work on estimating metabolic costs from portable wearable sensors. This work was done in collaboration with 3 advisors: David Remy, Dan Ferris, and Elliot Rouse. And we've published this work in the Journal of Applied Physiology and the IEEE Robotics and Automation magazine. So I briefly described to you the method of human-in-the-loop optimization, where real-time measurements from the person wearing the assistive device are used to update the parameters of the control system. And this process has great potential for the customization of wearable robotic controllers. It's been demonstrated a few different times using different optimization algorithms and different assistive device hardware. But the common thread between these studies so far has been that they all seek to optimize for the user's energy expenditure, or find the control parameters that minimize the user's metabolic cost. So this means that real-time measurements of metabolic cost are required for these algorithms to proceed. And to date, all studies that have used human-in-the-loop optimization have utilized indirect calorimetry to obtain these estimates. So indirect calorimetry is a system that measures a person's oxygen consumption and carbon dioxide production at the mouth. And these 2 quantities can be converted into a measurement of energy expenditure. So pictured here is the top of the line system. This is the Cosmed K5. It's wireless and portable from the computer, but as you can see, it's a very obtrusive sensor. The user wears a rubber mask over their nose and mouth that contains an embedded flow meter. There are gas sample lines that come from the mask and go into the processing unit, which is carried around by the user wearing a harness. So this bulky sensor, rubber mask covering your nose and mouth means that indirect calorimetry is not suited for long-term data collections outside the lab, and certainly would never be worn during an individual's activities of daily living. So in addition to the bulky and obtrusive sensing equipment, measurements obtained through indirect calorimetry are noisy and sparsely sampled. We only are able to get one data point per breath. In addition, estimation of steady state energy cost is dynamically delayed. So I'll illustrate this concept with a simple cartoon. For a step change in activity intensity, say you change walking speeds or you change the assistive control parameters, there's an associated step change in metabolic effort, or how much energy it requires for you to complete a task. And we call this quantity the ground truth energy cost. And this one value, the ground truth energy cost, is what we want to measure to give to the optimization algorithm. But using indirect calorimetry, it can take approximately 6 minutes to get a good estimate of this ground truth value. Now, although this is a cartoon, this is real data, and so you can see how noisy these measurements are. There are some modeling techniques that can reduce this time, but current implementations of human-in-the-loop optimization still require about 2 to 3 minutes of data collection per parameter setting, which means that these routines can take a long time and the number of settings that we can sample are limited. So as an alternative, we were interested in using physiological signals collected from portable wearable sensors to estimate this ground truth energy cost. Now, this method has the potential to estimate ground truth energy cost faster, as well as without the bulky mask. And both of these things are necessary for the translation of these methods outside the lab. So to begin this work, we needed to collect a large data set for analysis that included subjects wearing lots of different portable sensors, as well as collect a ground truth energy cost using the indirect calorimetry system so that we could build our predictive models. So for analysis purposes on our end, we grouped the signals into larger categories. We called one group of signals that we analyzed the local signals. These signals were the limb accelerations and EMG signals. And we called them local signals because they provide information about one particular body segment or muscle, and they kind of provide mostly kinematic information. Now, the global signals was the second group, and these included signals like heart rate, electrodermal activity, skin temperature, breathing frequency, minute ventilation, and oxygen saturation. And we called them global signals because they give information about the general state of the physiology of the user. So this data set includes people performing 6 activities: level walking, incline walking, backwards walking, and running on a treadmill, cycling on a stationary bike, and stair climbing on a stair mill. And subjects performed each of these 6 activities at a variety of speeds and intensities for 6 minutes each. So in total, this data set includes 187 6-minute trials. I'll mention this again later, but this data set is available open source if you have any use for it. So in the first analysis we did with this data set, we used multiple linear regression algorithms to predict ground truth energy cost from various subsets of the physiological signals. So out of the large sensor and signal set we collected, part of this analysis was determining which signals contain the most predictive information when only a small number of signals are included. And we did this intentionally because not all experimenters will have access to a large number of sensors. And additionally, people will not want to wear like a full suit of sensors in their daily lives. So we wanted to analyze, if you're only going to use 1 through 8 signals, which are the most important. So this figure shows the root mean squared error is shown RMSE on the y-axis between the predicted energy cost and the actual energy cost. On the x-axis is the number of predictors that we included in the regression from 1 signal up through 8. So using only 1 signal, the best predictor was minute ventilation, which is defined as the volume of air breathed per minute. So with minute ventilation, we could get about a 1.2 watts per kilogram error between our predicted ground truth energy cost and our actual. And as you can see with this figure, adding more signals improved the prediction error, but with diminishing return. When we look more closely at the linear regression algorithms that were trained with the best signals, or those that were highly correlated with energy cost, signals like heart rate, minute ventilation that I just talked about, and the limb accelerations, we noticed that the speed of the prediction of our ground truth energy cost was limited by the dynamics of the input signals. So in fact, signals like heart rate and minute ventilation have individually been characterized as first order systems with time constants of 58 and 53 seconds, respectively. So this means that there's a delay in these signals before they reach a steady state. So using dynamically delayed input signals in linear regression will produce dynamically delayed predictions of our ground truth energy cost. So to address this, we looked into the mathematical structure of the first order model, where Y is the input or the physiological signals, and X is the output or the energy cost, the thing we're trying to predict. So rearranging this equation for the output, X, we noticed that it takes the form as a multiple linear regression trained on the signals Y and their derivatives Y dot. So in the analysis I'd like to share with you, we wanted to evaluate the effect of including these derivatives in the multiple linear regressions on the prediction of ground truth energy cost. So we tested 6 different sets of input signals, the local, global, and combined signals. And the combined signals are just all of them, the local plus global. And we trained models with just the signals and then the signals plus their derivatives, and we compared the the performance of these models. So one of our main findings was that including derivatives in the regression improved the prediction magnitude or reduced the error of our prediction. So in this figure, time is on the x-axis and represents the duration of a trial for 5 minutes. Mean absolute error, or MAE, is on the y-axis. And for each of the 187 trials, we calculated the MAE as the predicted energy cost subtracted from the ground truth, and then we averaged it over all of the trials. So the local signals are shown in blue, the red signals are the global signals, and the combined signals are shown in yellow. The solid lines depict the models that are signals only, and the dashed lines indicate those that are the signals plus their derivatives. So the main thing that we noticed is that including derivatives in the magnitude of the prediction error, the main thing that we noticed is including derivatives improved the magnitude of the prediction error, especially in the first minute. And this effect was most pronounced in the global and the combined signal groups, and the local signals were less affected. So in the first minute, including derivatives in the regression model reduced the average error by 32.5% for the global signals and 25.4% for the combined signals. The other main finding of our study was that including derivatives in the regression model improved the speed of predicting ground truth energy cost. So as a metric of speed, we looked at the time to 1 watt per kilogram, or how quickly does the error fall below the threshold of 1 watt per kilogram. And we chose 1 as a threshold for this study because it represented 10% of the entire range of metabolic cost across all activities, but it is relatively arbitrary. It would be up to individual experimenters to decide, what's an appropriate threshold for error. As I said, in this study, we looked at time to 1 watt per kilogram. And here that we see that very large time savings are possible, including derivatives in the prediction. So we see that the global signals reached 1 watt per kilogram 40 seconds faster when derivatives were included, and the combined signals reached 1 watt per kilogram 29 seconds faster. The local signals were unaffected in this analysis. As you can see, those predictions never even fell below the 1 watt per kilogram threshold. So these results show us that simply including derivatives in the multiple linear regressions can be responsible for large time savings. In this case, we saw about 30 to 40 seconds when trying to achieve some acceptable error threshold. So to summarize the results I just presented you for this portion of the work, we found that we could achieve pretty good prediction of ground truth energy cost from a small number of simply processed signals. We also found that adding derivatives for free, meaning you don't need any additional equipment and it requires minimal processing to calculate a derivative. So adding derivatives can improve the speed of prediction in a black box algorithm like linear regression. And one of the benefits to this is that you don't need an explicit model of signal dynamics in order to achieve this. And this can be especially useful when the input signals are dynamically delayed, like many of the physiological signals that we used in this study. There's still a ton of work to do here, especially to achieve estimation of energy costs that is fast enough and accurate enough to use in human-in-the-loop optimizations outside the lab. There's certainly no limit to the algorithms and features that can be explored. So if you are interested in this work or see another way that this data could be useful to you, please use it. The data set is available open source and it's hosted on BigShare. So in chapters 3 and 4 of my dissertation, which I presented just a brief subset of the results here today, I presented the first studies to our knowledge that used portable sensors to predict steady state or instantaneous ground truth energy cost. And this is a necessary step for the translation of human-in-the-loop optimization algorithms outside the lab. This work resulted in a large open source data set that is intended to accelerate the translation of these algorithms by enabling other researchers to build their own predictive models. In the study that we published in the Journal of Applied Physiology, we presented a systematic evaluation of the salience or predictive capability of individual signals and groups of signals. We also evaluated which signals or groups of signals are robust to predicting energy costs from unknown subjects or unknown activities, which again is important information for human-in-the-loop optimization. In the study published in the Robotics and Automation magazine, we demonstrated that including the derivatives of the physiological signals improves both the speed and accuracy of prediction, especially when the signals are dynamically delayed. And finally, we also presented a mathematical framework to compare the coefficients of explicit models to black box regression models. And this mathematical framework can certainly be expanded in the future. So that concludes my discussion of chapters 3 and 4. So I would like to move on to the last chapter, chapter 5, which focuses on evaluating user preferences in ankle exoskeleton controllers. So this work, which is titled User Preference as a Holistic Objective for the Control of Robotic Exoskeletons, was completed under the advisement of Elliot Rouse and David Remy. We presented pilot data for this work at the 2020 BioRobe conference, and a full manuscript is currently in review for publication at Science Robotics. So as we've already discussed, for ankle exoskeletons, and in particular those aimed at augmenting able-bodied walking, the most common goal for these devices is to reduce the user's energy cost. And this cost function is somewhat intuitive and absolutely has relevance for assisting users during long bouts of walking or running, right? The less energy a person consumes, the more efficient their gait becomes. They can walk farther or run faster or carry a heavier load. But a challenge with human-in-the-loop optimization paradigms that minimize energetic cost is that they require that we predefine one single measurable physiological cost function that maintains relevance in all situations. But again, when we consider the ways that individuals may use exoskeletons in their jobs or in their daily lives, it's likely that users prioritize many different objectives simultaneously. They care about things like balance or effort or comfort. And individually, these metrics can be difficult to quantify, but one way to capture some of them is to ask users about their preference. So user preference likely encodes relevant information from multiple sources that are all related to the user's experience wearing the device. And we believe that incorporating user preference into exoskeleton control systems has the potential to increase user satisfaction, promote acceptance of the robotic device, as well as add a rich source of holistic information that cannot easily be measured using standard biometric sensors. Since user preference as a control objective for robotic exoskeletons is relatively new, we wanted to inform future preference-based control frameworks by first answering some more fundamental questions about user preference. So the goal of this study was to measure and analyze users' preferences in the applied torque characteristics of bilateral robotic ankle exoskeletons. We were interested in understanding what assistance characteristics users prefer. Are they unique among users? And then how precisely or repeatably can individuals find their preferences? We also wanted to characterize how preference varies with walking speed, how it varies as individuals learn and adapt to the robotic assistance, and then finally, how does preference vary between individuals with different technical backgrounds? So in this experiment, subjects wore bilateral ankle exoskeletons that were manufactured by Defy. These exos can provide plantar flexion torque by spooling up a cable that using the actuator that's mounted to the shank. So this means that this device can push your toes down like you're pushing on a gas pedal. And these devices are autonomous, meaning they're not tethered to anything. So in this experiment, subjects walked on a treadmill with a touchscreen tablet mounted on the rail in front of them. And this tablet displayed a blank two-dimensional grid like is shown here. So using the touchscreen, we asked subjects to self-tune their exoskeleton assistance profile in order to find their preference. So in this experiment, the assistance profile was exoskeleton torque as a function of the user's gait cycle. And it was characterized by two parameters, the timing of the peak torque, as well as the magnitude of the peak torque. And as you can see on the left, the two parameters on the axes of the grid are mapped to the assistance profile on the right by commanding the two parameters. So touching the grid instantaneously changes the torque profile that the user experiences. Now this is what's happening behind the scenes, but what the subject sees on the screen is just a blank two-dimensional grid. So subjects were asked to explore the grid to find their preference. The axes were hidden from the subject as well as randomized between each trial so that they didn't just return to the same XY location on the grid. Subjects would start at a random initial condition, which is indicated by the red circle. And then they were instructed to just explore the space to find their preference, the way that they preferred the exoskeleton to assist them. So when they found their preference, which is the green asterisk, they informed the experimenter and we stopped the trial. So this process constituted one preference identification trial. In the actual experiment, the subject just saw the crosshairs on the screen to indicate the settings that they had explored. I connected them here with lines just for visualization. So in this study, we had 24 able-bodied subjects perform this experiment. 12 of these subjects were naive users, meaning they had no prior exoskeleton experience. And 12 of them were knowledgeable users who were researchers in the field of wearable robotics. And some of these knowledgeable users also had experience walking in powered exoskeletons. So each subject performed 8 repeated preference identification trials. The naive cohort performed 8 trials at each of 3 speeds, and the knowledgeable cohort performed 8 trials at 1 speed. As I mentioned, subjects were instructed to kind of explore the grid to confirm that they were finding their actual preference, but we didn't enforce any time limit on their exploration. So shown here are the results from naive subjects finding their preferences pooled across all of the 3 speeds that they performed. So this is pooled across 24 trials. In this experiment, naive subjects repeatably and reliably identified their preferred settings in 2 dimensions. So pooled across all speeds, each subject's average preferred timing and magnitude. Timing is on the x-axis and magnitude is on the y. And each subject is shown as a different colored square in this figure. The error bars are the 95% confidence intervals for each parameter. And the main thing to notice here is that subjects were unique in their preferences, especially in magnitude. You can see that subjects' preferences are spread out, continuously across the y-axis, whereas subjects were more similar in their timing preferences. They're clustered between kind of a 55 to 59% of the gait cycle. Subjects were also precise identifying their preferences. The mean within subject standard deviation of preferred timing was 1.53% of the gait cycle, which corresponds to just a time window of 17 milliseconds. The mean within subject standard deviation of preferred magnitude was 1.47 Newton meters, which corresponds to about 1.5% of the peak ankle torque produced by the biological ankle during walking. And this precision is pretty impressive because remember, subjects were blinded to the axes of the grid, they were randomized and rotated each trial. And so they really had to explore and customize their controller based on their own perception of the device assistance. Finally, subjects identified their preferences quickly. They explored for a mean time of 105 seconds or just 1.8 minutes before selecting their preferences each trial. So shown here on the right is each user's preferred torque profile, and that was generated according to their mean preferred parameters. This is the same data, just another way to visualize it. And again, we can see the variability in the height of the peaks or in the magnitude preference, and we see more consistency in the timing of the peak torque. So to understand the next results about how speed and trial block affect user preference, I'd like to give you just a little bit more background about how this experiment was run. So we had 12 naive subjects who performed testing at each of 3 speeds. And we block randomized the order of the speeds that each subject performed in order to balance out the data set. So for example, subject 1 might have performed the speeds as nominal, slow, and then fast, while subject 2 might have performed them fast, nominal, and slow. So when we analyze the effect of speed, we just group the subject's data from that particular speed condition. But there's a second factor here, which is trial block, or the order that the speeds were presented. So each subject performed 3 blocks of 8 trials, where trial block 1 was trials 1 through 8, 2 was 9 through 16, and trial block 3 was trials 17 through 24. So we also grouped the data according to trial block, and this allowed us to evaluate how does preference change over the course of the experiment as individuals learn and gain experience walking with the device. So here we can see a 2-dimensional plot of preference data. So the subject's preferred magnitude is on the z-axis, and speed and trial block, our 2 factors, are on the x and y axes. So to analyze these data, we use linear mixed effects models. And in these models, we have the outcome y, which is the preferred magnitude or the preferred timing. And then we use the 2 fixed effects we just discussed, speed and trial block. And these models also contain a random effect for subject and an error term, but we're not going to discuss those in detail here. So this model generates a 2D surface that best fits the data as shown here. And the cool part about this model is that solving for the coefficients in front of the fixed effects, which is shown in this equation by the capital letter Z, provides the slope of the model with respect to speed and an associated p-value, and a slope of the model with respect to trial block and an associated p-value. So in our study, we use a significance threshold of 0.05. So if the p-values of these terms are less than 0.05, we would say that the slope of the model for that fixed effect is significantly different than 0. So because this is a 3D plot, in the next plots, I will show you the 2D versions of them. And so you'll see these purple and teal gradient lines. So these gradient lines correspond to slices of that surface at either 1, 1.2, and 1.4 meters per second, or the first, second, and third trial blocks, depending on which 2-dimensional direction we're looking at it from. So here we're looking at a 2D slice of that 3D plot that I just showed you. There's a little cartoon cheat sheet on the side there. So what we're looking at here is preferred peak torque magnitude plotted on the y-axis and walking speed on the x-axis. So the light gray lines you see are individual subjects' preferences across speeds. The black squares and error bars are the inter-subject mean and standard error. And again, the purple lines are the slope of the linear mixed effects model, which have been sliced at trial block 1, 2, and 3. The p-value for this slope is shown at the top, which is 0.06. And so this tells us that the preferred peak torque magnitude did not significantly increase with speed because it's greater than 0.05. Now this p-value is borderline, but the effect is small. And even if this was significant, we would only expect an increase of about 0.5 Newton meters over the range of speeds tested. So now if we look at preferred peak torque magnitude with respect to trial block, we see that the p-value is significant, 0.01. And so this tells us that preferred magnitude actually increased with trial block, or increased with how long the subject interacted with the device. Now, the nice thing about the linear mixed effects model is that it allows us to calculate a slope. And so we can definitively say that this model predicts that users prefer 1.5 Newton meters higher peak torque from the first to the last trial block. These are the same plots, but instead I am showing you preferred peak torque timing on the y-axis. So we see that the p-values for both speed and condition order are 0.44 and 0.56, which tells us that preferred timing did not significantly vary with speed or with trial block. An additional analysis that we performed in this study is to compare the preferences and precision, or standard deviation, of the 12 naive subjects to the 12 knowledgeable subjects. Just as a reminder, the naive subjects had no prior exoskeleton experience, and the knowledgeable subjects were researchers in the field, and some of whom had prior experience walking in powered exoskeletons. So we compared the 8 preference identification trials that each group performed walking at 1.2 meters per second. And the key finding here was that knowledgeable subjects preferred significantly higher peak torque magnitude than the naive subjects. We did not find differences between the groups in preferred timing or in precision, identifying either their preferred magnitude or preferred timing. So to summarize the findings I presented here, exoskeleton users quickly and precisely identified their preferred assistance in 2 dimensions. We found that naive users preferred higher torque as the experiment progressed. And we also found that knowledgeable users preferred higher torque magnitude than naive users. So I hope a full manuscript is forthcoming soon. And the larger analysis in this manuscript includes a discussion of subjects' precision at different speeds or trial block, as well as looking more deeply into their touchscreen exploration strategies. So in chapter 5 of my dissertation, I presented my work evaluating user preference as a holistic objective for exoskeleton control. We believe this is the first study to demonstrate that users can quickly and reliably identify unique preference in the characteristics of their ankle exoskeleton assistance in 2 dimensions simultaneously. And we believe that this result has implications for the field because it motivates new strategies for the control of lower limb exoskeletons, where users can customize the assistance according to their own unique preferences. This study also features a rigorous analysis of the characteristics of user preference in the context of exoskeleton control. So for this reason, this study is a first step towards discovering how individuals perceive, interact with, and learn from the assistance provided by robotic exoskeletons. So I would like to finish my presentation today with a brief summary and some future directions for this work. So as a whole, my doctoral work evaluates the notion of optimality in the control of wearable robotic devices. And I believe it also lays the foundation for translating optimization protocols outside the laboratory environment. So the work I've described today explored different cost functions for the optimization of wearable robots, as well as presented new measurement tools to obtain accurate estimates of the necessary physiological and subjective quantities. The work I presented today contributes to each phase of this optimization pipeline, and I hope that it paves the way for future research advances in each of these areas. So for estimating metabolic costs using portable sensors, the biggest thing in the short term is minimizing the prediction error to a point where the estimate is reliable enough to replace an indirect calorimetry system. So this means exploring new predictive algorithms, new features, signal processing techniques, that sort of thing. And we should really focus on the speed and accuracy of these predictions in order to really enable their use in human-in-the-loop optimization routines. More generally, the future direction for this work is using wearable or unobtrusive sensors to estimate any number of different physiological or subjective quantities of interest. This is a very broad goal, right? There are probably an infinite number of ways to apply it, but it's something that we can consider for the translation of assistive devices. For the user preference study, some next steps include diving more deeply into the psychophysical nature of user preferences. So for example, how well can users sense changes in magnitude or in the magnitude of torque assistance or timing of torque assistance? And understanding quantities like the just noticeable difference of these assistance characteristics might provide insight into how to design future controllers, like what degree of resolution might be necessary to provide the user, as well as teach us fundamental things about the human neuromotor system. So the broad future I see for this work is incorporating user preference as a metric in a multi-objective optimization. So you could consider giving the user autonomy to choose the assistance that feels best for them out of a group of maybe 3 assistance trajectories that produce similar reductions in energy cost. Or we could consider including user preference in the loop and designing controllers to automatically predict and adjust to the user's comfort. So throughout this talk, I have shared with you my work starting to think about the question, how do we provide users with optimal assistance from robotic exoskeletons and prostheses outside the lab? We discussed replacing bulky laboratory sensors with portable ones and using sensor fusion algorithms to estimate relevant physiological quantities. And we discussed alternate objectives for exoskeleton control, such as user preference. And I believe that ultimately the answer to the question about optimal assistance will include multi-objective optimized assistance and consider both elements from the user's physiology as well as their comfort and preference. So before answering your burning questions, I would like to take a moment just to acknowledge some of the parties that helped make my graduate career a success. First, thank you to the funding agencies who supported my research, the NIH, the NSF, and the Graduate Research Fellowship, and the Rackham Graduate School for their conference travel support. Thank you to my wonderful committee, David Remy, Elliot Rouse, Deanna Gates, and Noel Perkins. Thank you to my study participants, my collaborators, especially at Defy, and the colleagues who made this work possible. I would especially like to acknowledge the members of the RAM Lab and the Neurobionics Lab and thank them for all the fun and support over the years. Most people get 1, maybe 2 lab groups in their graduate career, and I'm lucky enough to have had 4 groups that welcomed me. So thank you also to the members of the H&L at both U of M and Florida, and to the members of the RBL. I am very lucky to have been trained by the best at Shirley Ryan Ability Lab and to have the opportunity to keep collaborating with them during my time here at Michigan. Thank you especially to Annie Simon and Levi Hargrove. Yes, grad school is a lot of work, but you get through it with the support from friends. So thank you to those pictured here and everyone not pictured here for making my time in Michigan so special. And finally, thank you to my family. I am grateful for my partner, Casey, and our little cat, Maisie, and for the rest of the Bantle family, especially Pat, Ray, and Marge. And thank you to my family, especially my parents, Dave and Gina, who are watching from the other room. I would not be here without you. Boring references, publications, and I would love to take any questions.
Let's give Kim a round of applause. Good job, Kim. That was great. We can now take questions from the audience. Feel free to unmute yourself, raise your hand, or post questions to the chat.
Elliot, there are some in the chat if you want to read them.
Oh, thanks. This is a question from Daphne. This is a question about using preference-based tuning. Is there the potential for this type of tuning to magnify existing or undesirable attributes of subject's gait? If so, could multi-objective optimization mitigate this?
Yes, I think this is a really important question that comes up a lot when we talk about preference, because there's sort of the impression that like people don't really know what's good for them. And so one way to think about this is to try to figure out what other biomechanical or physiological quantities preference either correlates with or maybe is the same, right? Do people prefer the things that minimize their energy cost? Some of my colleagues in the neurobionics lab, Tyler Kleitz and Max Shepard, did a study with the variable stiffness prosthetic ankle that started to look at these questions. They found that user preference did not correspond to minimizing energy cost, but we don't know if that's the same for ankle exoskeletons. And so certainly I think understanding how user preference controllers relate to other state-of-the-art controllers in our field is really important. And then I think, yeah, multi-objective optimization where maybe you don't give the user full control, but you allow them to make adjustments within a range of possibilities to still allow them to optimize for their comfort, maybe within a more constrained environment to still guarantee some biomechanical or physiological effect.
Great, thanks, Kim. We have another question in the chat from Kathy. It's how quickly did the torque change when the subject picked their preference on the tablet? And did you recheck the naive wearers after they went through the original study? If so, did their data match the knowledgeable data?
Yeah, those are great questions. So the torque changed, I would say, as instantaneously as possible. So it would change the next heel contact. So the next time the subject's heel hit the ground, the new torque profile that they chose would take effect. So they couldn't change more quickly than once per step, but we actually encourage subjects to take maybe 3 or 4 steps per setting to really kind of evaluate it anyway. Rechecking the naive wearers after they went through the original study, we did not do that. The thing that's interesting about, like, you picked up on the idea that if we give naive users enough practice, eventually they'll converge to the preference of the knowledgeable users. And that's something that we thought also, and it's definitely a possibility. It would be interesting to check more time points to see how that evolves. But the other interesting thing is that not all the knowledgeable users actually had experience walking in the device. Some of them were just researchers, you know, in the lab or in the field who had maybe some like preconceived notions or internal knowledge of exoskeleton control. And so we actually think that some of their prior experiences also might have shaped or influenced their preferences with the control. So I think that's 2 kind of interesting paths for exploration.
Great. We have another question from the chat from Rachel Hybart. It says, if you brought a subject back a second time and set the initial torque to their final preferred torque from the previous session, do you still think you would see a significant increase in torque magnitude over time, or would it stay closer to that final value? Similar question. Yeah,
this question is asking about kind of the asymptote of learning, right? If you give people experience, when does their preference begin to level out to say, you know, this is their final preference? We don't know yet. We don't know if it asymptotes. We don't know when it asymptotes. We don't know what kind of maybe directed experience is required to have people maybe converge on a fixed preference. So these are all great observations that you guys really understood the study. So that's fantastic. Yeah, thank you.
Other questions? Going once?
I have a question, Kim.
Thanks, Nick.
This is not meant to be a hard one, but it may sound hard. But The preference, I really liked your figure where you had in the intro for your preference study, you had this net around all these biomechanical things that could explain preference, right? So my question is, basically, this idea of energetics versus preference, but like in this study, so balance, comfort, stability, pain, effort. Yeah, like so pain would be hard to measure with something biomechanical, but the others, for sure, you could get something kind of close. So my question would be, do you think that you could sort of fit, is there enough data that you've collected or, that study or in a future study to explain preference from these biomechanical factors? So, maybe it isn't that holistic, like maybe it is kind of consistent and it's just a different biomechanical metric than energetics.
It definitely could be. Honestly, that is sort of the ideal situation, right? Stability, let's say stability is the thing. It is really hard to measure stability. Nobody agrees on how to do it. We have static, we have dynamic, we have all these different metrics of stability. So if preference is just a proxy for one thing like stability, great. That is so much easier and so much better. So I don't think that's really what's going to happen. I think it's more likely that it is a combination of lots of these things. And then there's two approaches to think about that. One is, can we identify and measure each of these things and build some sort of like regression out of it, right? It's this part stability plus this much balance plus this much effort equals preference. That's one option, probably the harder option, but it has the opportunity to teach us interesting things. The other option is something black box, right? Can we predict preference from kinematics, kinetics, from other measurable things that we don't necessarily care if that's an accurate representation of preference. It's just that it gets us the quantity that we need. So I think there's a couple different ways to think about it depending on your goals and what you want to learn.
That'd have to probably be in a new experiment, right? Where you extremely, like highly sensorize someone to with mocap and with, yeah, lots of different things, right?
Probably a fusion of the two experiments that I discussed. But yeah, in this study that I performed with preference, we didn't collect metabolic cost, kinematics, kinetics, any of that additional data. So it would require a different data collection, some sort of like maybe parameter sweep or some other clever way to compare them.
We have another question from the chat. This is a question from Jacob Baum. Do you think user preference can be shaped to be the most optimal in terms of energy or biomechanics, i.e. have multiple sessions that start at user preference and follow a path towards the most optimal?
Yeah, this is very interesting. This reminds me a lot of like sort of Max Donelon's work in the idea of, can we force to some degree, or like, can we allow the human's neuromotor system to adapt in a directed way towards a way that we want them to? I think it's absolutely possible, but it's not something that I've thought critically about yet. But I love that idea. I think it's really exciting.
Great. Last call for questions.
Yeah, I'll hop in. Kim, great talk, amazing work. I'll just throw out, I guess, another, especially while we have this slide up, a question about how this stuff translates to people, because the preferences are so diverse. So was there anything surprising that you found that you think we still have a bit of work to go before engineers can sort of address sort of these end user needs? Like, was there anything surprising about how people either talked to you after experiments about how they experienced the sort of process of learning or training, or what they thought would be cool that you're like, that's neat, but we're not quite there yet.
Yeah, I think that something that was interesting is in the preference study particularly, I read them a script at the beginning. So it was like, the goal of this device is to assist you while you walk. It helps you by pushing your toes down. Select your preference. And then people would ask me, well, what do you mean? And I would say, what do you prefer? Like, we very carefully crafted that as to try and not bias them towards what they would be sensing and trying to decide. So we were like, your preference, up to you. And I do think that different people throughout conversations and feedback that they gave me interpreted that differently. One person said at the end, they kind of tuned the power down quite a bit, the magnitude, and said, I'm an able-bodied person. I walk just fine. I don't need assistance. So you asked me to find the one that I prefer. I turned it down. That's a valid interpretation of the prompt, right? Other people were like, I don't want to do any work. I want this thing to do the work for me. I want to ride it and have it help me. And so they turned the power all the way up, which is another valid interpretation of the prompt. So I think that the other thing is, I think that also contributed to the difference we see between the naive and the knowledgeable users, that maybe the knowledgeable users, who are people exposed to exoskeleton control every day, have internalized, like, this device can help me in some way. If I utilize the power, it can help me. Whereas maybe people who aren't familiar with exoskeletons for able-bodied augmentation would say, like, I don't really need this. And so I think that the education in terms of like the benefits of the device and just knowledge of like what the device can do and how it can help you, I think that was a big discrepancy between subjects and how they interpreted what does preference mean to them.
Sure. Cool. Thanks so much.
Okay, last call for questions.
I have one real quick.
All right.
So along the lines of those past couple questions, was there any indication of maybe a lack of trust that, you know, maybe the exoskeleton, if I turn it up too high, may break my ankle? I'm just thinking of how, you know, the torque went up both with experience, but also with time. And if you got any indications of kind of that lack of trust in the device that grew and helped them turn up the torque.
I'm not sure. I didn't ask them specifically about trust. So I think that's an interesting point. I did my best to educate them, you know, through the IRB protocol about the risks. And, you know, we walked through the hard stops on the device as well as the control safety mechanisms and that sort of thing. So I'm not sure that I would characterize it as trust, but definitely I think the time effect that you pointed out of being more willing to accept assistance the longer they interacted with it. I don't know what mechanism is necessarily driving that. It could be trust or confidence in that it's not going to hurt you if you keep turning it up. And then it also could just be just a neuromotor adaptation to the assistance. It can be unsettling or jarring the first time you walk in it because you're just not used to having it. So I definitely think there's some adaptation elements, whether or not that's driven by fear or trust, I'm not totally sure.
Thank you.
Great. Let's give Kim one more round of applause. Congrats, Kim. Now we will kind of enter the more private question and answer session. So everyone, this meeting is over. People can leave this session, and then if people exit, we'll create a breakout room and get to a smaller room with just Kim and the committee.